Thank you. I'm going to talk about probabilistic PDE solvers, which is a lovely, relaxing way to start our first day. PDE solvers maybe are not quite so familiar to everybody as linear solvers, given that they're not sort of core to everybody's mathematical education. So perhaps I can start with a straw poll of who would consider themselves to have a good amount of experience with solving PDEs numerically or analysis-wise. Okay, so quite a small number. So it's probably good then that this talk is not very fast-paced, and we're going to go through things quite slowly and hopefully get quite a lot of motivation and intuition for what these probabilistic solvers look like and how they relate to standard classical solvers, as we would call them, for PDEs. So I have 5 sections here. We're going to start by getting ourselves really motivated for the topic of solving PDEs. Then we'll talk through in sections 2 and 3 how we get from what we've seen so far, so basically GP regression plus probabilistic linear solvers to PDE solvers. In section 4 we'll do a tiny bit of not particularly intimidating theory, hopefully not too intimidating theory. And then finally in section 5 we'll talk about some of my work in applying these solvers to solve Bayesian inverse problems. So yeah, let's start with some motivation. So basically the motivation for why we might be interested in probabilistic PDE solvers is twofold. Firstly, that PDEs are everywhere. In scientific computation, it's fairly easy to find cases where we might want to solve problems that are related to the solution of PDE, for example, estimation problems, and we'll see some examples of where that comes up in the next few slides. But secondly, that PDEs are very, very hard to solve. So this is where probabilistic numerics is hopefully going to come to the rescue, at least after a little bit more research than where we are currently, in allowing us to relax the amount of computation that we're putting into solving these PDEs while still being able to answer the fundamental mathematical questions related to solution of PDEs that affect so many aspects of everyday life. So, given that very few people put their hands up when I said who's familiar with PDEs, we're going to start with a slide where we really talk about what a PDE actually is. Hopefully this is going to be refresher material for most of you, but again we'll go quite slowly, so if it's not familiar, hopefully you'll end this slide and the slide after it knowing everything about what a PDE is at least. So in a partial differential equation, in this slide I'm going to use the heat equation as a motivation. So the sort of scientific problem that we might be interested in and that we can model with the heat equation is suppose that we've got a bar, and in this case I'm going to use a bar that is one-dimensional, so it's just a line. This pointer really doesn't work at all, does it? So I've got a one-dimensional bar. I'm going to use my digital pointer. That's just a line, so the interval from 0 to 1. This function u is telling me what's the temperature at each point in that spatial domain. So I've got my domain from 0 to 1. U of x is the temperature of this one-dimensional bar at each point from 0 to 1. And I've also got a temporal dimension here from 0 to capital T. So we're going to be looking at how the temperature of that bar evolves over time. So that's my u here, u of x and t, and it's a function that goes into r. Technically it should be r plus. Well, no, actually we're doing heat, so it can be negative. That's fine. So the equation that tells me what how heat evolves along this bar is this equation here. This is what's usually referred to as the heat equation, which says that the first derivative of this function with respect to time is equal to the second derivative of this function with respect to space. So that is a description of how heat evolves along this bar, but this isn't enough for us to identify the solution to this PDE exactly, because only knowing the derivative of a function, there are infinitely many functions which have the same derivatives. For example, we could just do a vertical shift of the function and we would get a function with the same derivative. So we need some extra information to identify the solution to this PDE, and this is given to us in what are usually called boundary conditions. So in this particular version of the heat equation, I usually have 2 boundary conditions. The first of them is actually normally called an initial condition because it tells me what the heat distribution in this bar is at the initial time point, at time t0, or time t equals 0 in this case. So here I'm saying I know what the distribution of heat is in this bar at time 0, and it's u0 of x. So that's telling me sort of on one line at the initial time point, one sort of side of the domain, what the function is. But we also need some information about what the function looks like on other parts of the domain to give me a well-defined solution across all of time. And that's given to us in the form of, in this case, these are called Dirichlet boundary conditions. Dirichlet just means that I'm observing the function's value directly at the two ends of the bar. So in this case, I have a unit interval bar, and I'm observing that u at the left side of the bar at x equals 0 is equal to a, and u at the right side of the bar is equal to b. So we could still set up this PDE with other boundary conditions and get a unique solution. A boundary condition that people often work with are called Neumann boundary conditions, which is kind of like if we assume that we have insulated the ends of the bar so no heat can get out through the ends. In this case, I'm just assuming Dirichlet boundary conditions. So these boundary conditions can be thought of as a bit like if I've attached heaters to either end of the bar, and the heater on the left is applying a heat at A degrees through the bar, and the heater on the right is applying a heat at B degrees through the other side of the bar. So we're going to look at how this solution evolves over time. So this is the plot that I have here. So if I start this going, this is a simulation of the solution to the heat equation, just using the finite difference method, which, if that doesn't mean anything to you, don't worry about it, for, I think, the first minute or so of time of this heat evolution. So we can see that A and B here, the heats that I'm applying on the left and right sides of the bar, are both equal to 1, which is where this sort of sinusoidy, wiggly curve is centered. And the initial heat distribution I've just set to be a sinusoid plus 1. So it's not a particularly interesting solution. As time goes on, because we're heating at a constant rate at each end of the bar, but we haven't done anything to stop the heat from escaping the bar just sort of evolves to, at T is 0.2, a constant temperature equal to the amount of heat that I'm applying to each end. So that's what a PDE is. It's an equation which describes an unknown function in terms of its derivatives, plus usually some boundary conditions which give me the ability to identify the function exactly, which I'm not able to do with just this equation describing the derivatives. Okay, so the sort of point of this first section is why a PDE is important, and the first part of that is basically similar to what, I can't remember if it was Philip or Jonathan said in their talk. PDEs are everywhere in scientific computing. Linear solvers are also everywhere in scientific computing. PDEs are perhaps a little bit less everywhere in scientific computing than linear solvers, but still very, very important. So I've got 3 examples of actually practically useful PDEs that people are solving on a day-to-day basis that have a real, well, in some cases at least, a real importance in our everyday lives. So the first one is in engineering. So on the right side of this slide here, again, digital pointer, these are the linear elasticity equations. I'm not going to dwell on the specific form of these equations too much, apart from to say what they describe, which is they describe how a displacement of a structure, so we can have in mind, for example, a bridge, which is what this picture is over here. This is the Millennium Bridge in London. The displacement of this bridge is related to external stresses, for example, due to wind or due to pedestrians walking across the bridge, and internal strains, which are the forces which cause these displacements of the bridge. So those are the equations, which you don't need to worry too much about, but what are they actually practically used for? Well, if I design a structure, unless I have some physical model of how the structure behaves in response to stresses, I have no guarantee that my structure, when I build it, is not just going to fall over like a house of cards. And clearly, that's something we would prefer not to happen if we're talking about a bridge or a building or so on. And indeed, if I start this video that I've got on the slide here, we can see that when the Millennium Bridge was first constructed, because the forces that were being applied to the bridge had not been sort of completely explored through the analysis that people did of the structure, it was nicknamed the Wobbly Bridge, which is a very inventive nickname for Londoners, because the movement of pedestrians across the bridge induced this sort of very pronounced and worrying wobble. Don't worry if you go to London now, because almost immediately after this was observed, they closed the bridge for quite a long time to install shock absorbers to stop this wobble. But nevertheless, this shows that if you don't have a sort of complete understanding of the physics, then there can be In this case, not disastrous, but in some cases, very problematic consequences. So the second example, perhaps a bit less of at least practical everyday use to people in this room, is in finance. My motivation here is that before I came into academia, I worked in finance and did a lot of solving the kind of equations that we're going to see on these slides. So we have a particular kind of contract in finance, which is called a derivative contract. And it's called a derivative contract because it bases its value on the value of a different financial asset. So in this case, we've got something called a call option. And the call option is a contract between a bank and a counterparty that, at its expiry, has a value that's based on the value of this underlying asset S, which is a stock. So the sort of attributes of this call option are an expiry. So that says when I'm going to check what the value of the stock is to decide how much I need to pay my counterparty, and a strike price, K. And the strike price is involved in the payoff. So this contract pays off the maximum of S of T minus K and 0. So this is quite an attractive asset, right? Because if I sell one of these call options to you, then the very worst case scenario is that at the end, you don't have to pay me any money. And in quite a lot of cases, I'm going to have to pay you some money. So these contracts are quite attractive in the sense that they have no downside. But of course, the bank always wins. So the bank charges the client an upfront cost for these contracts, which is sort of designed to offset the fact, the expected value, the expected payoff of these contracts at expiry. So that's what's described here. We denote the value of this call option at a time less than the expiry time as V of S and T. And perhaps you can see what's going to happen here, because this maximum here, this is a bit like a boundary condition. We know what the value of the contract is going to be at time T, and we'd just like to know what the value is for other times less than T. And in particular, as a bank, I would be interested in what's the value of this contract at time 0, which is where I'm standing now, the time when I'm actually about to sell this contract to someone, because that tells me how much I should charge the counterparty for it. So here I have a visualization of what the payoff of one of these contracts looks like. So on the y-axis here, I've got the payoff at time t, and on the x-axis, I've got the underlying stock price at that terminal time t, and the strike price here is k is 100. So we have this sort of what's usually called this hockey stick kind of payoff, where it's at 0 until we hit the strike price, and then it just goes up linearly with gradient 1. And of course, the bank doesn't want to have a contract that it's going to lose money on, so it will charge the counterparty an amount V S of 0, 0, which turns, if we think of a profit instead of a payoff at time t, this sort of drops the profit profile down by an amount that depends on how much the bank charged the counterparty for the contract at the initial time. Right? Okay, so although I talked about a boundary condition already, it's not necessarily clear how this really relates to PDEs, but probably most of you have heard of Black and Scholes, who showed that under some particular assumptions on how the stock price moves and some other assumptions, we can turn this problem of pricing this call option into the solution of a PDE. So in particular, we assume we're interested in the expected value of this asset. Standing at a time t smaller than t, what's the expected payoff at that future time t? And if we assume that the price of the stock follows this geometric Brownian motion, then we can turn this into the solution of a PDE, and it's actually basically just the solution of the heat equation again. Well, it goes via the solution of the heat equation again. This is not just the heat equation. So here we've got the PDE that describes how the value depends on the stock price in differential form, and here's the boundary condition, as I said before. So this Vt of S, this is my max of S of t minus k and 0. So at the terminal time, I know what the value of the contract is going to be. And if we just look at what that value looks like, so here again, this is the boundary condition, this orange hockey stick, the value of the option at its expiry. And if we look at some time less than t, we have this sort of characteristic relaxation of that continuous but not differentiable curve into something that's actually differentiable. So the third application perhaps has a little bit more importance to our day-to-day lives, which is weather and climate modeling. So down here I've got the solutions to a PDE, which is supposed to describe how air flows around the Antarctic. I think it's air, it might be the ocean, I'm not actually 100% sure. No, I think it's the air flows around the Antarctic. Here again, we can get to a PDE by modeling the ocean and the air as being the solution of a coupled set of partial differential equations for fluid flow. So here, the ocean, that's obviously a fluid, and the air we model as a fluid that's just much less dense than the ocean. So this is a sort of grossly oversimplified version of Navier-Stokes under an assumption that we have a Newtonian fluid, I think, that assumption is not always appropriate, particularly for climate models when we have turbulence, but nevertheless, again, you know, the same holds that we're not really necessarily interested in the form of the PDE so much as that there is a PDE under here. And the numerical implementation, the numerical solution of these PDEs is called computational fluid dynamics. So the idea is we can write down, if we know the initial conditions from, say, observations of pressure fields and temperature fields over the Earth, then we can initialize these PDEs with what the current conditions of the Earth are and simulate them forward to get an understanding of what weather is going to look like in the next few days or what climate is going to look like in the next few tens of years or hundreds or thousands of years potentially. Now, that's in an ideal world. The next section brings us to sort of the reality of how hard it is to deal with these PDEs, particularly in the last case where we have this sort of extremely complex multi-scale behavior, both in terms of the physics, the PDEs, and in terms of the domains that we're interested in. So let's first talk about how PDEs are currently solved. And apologies if you saw Marvin's little tutorial a moment ago, you will have seen some of this in a bit more detail than I'm going to go into. But at a sort of heuristic level, if we want to build a PDE solver, we need to turn this continuous set of equations and this sort of infinite dimensional object, the functional solution to the PDE, into something discrete that we can represent on a computer. So how that's usually done is, on the right here, I've got the sort of approaches that are usually taken in the Galerkin or finite element method specifically, for an aircraft wing in this case. But on the left, this is a more of a sort of general heuristic approach, which is, I would argue, what's the approach that's taken by most PDE solvers. So firstly, we represent the domain as a discrete object, either using, say, a grid or a mesh. So what I mean by a mesh here is we can see that I've got this aircraft wing, and I've basically put triangles all over it so that I can represent the entire continuous wing through these discrete set of triangles, which is called a triangulation of the mesh. Then we need to represent a solution on the mesh. And again, in FEM, what we do is we take these phi I, these are called basis functions, and we put one of them at each nodal point on this mesh, and then we create a set of functions by just weighting them. So these are the WIs. So if I want to represent a function that lives on this discretized domain, I just need to choose some weights, and that will give me a function. But crucially, this lives in a finite dimensional function space because I've got a capital N here. So I've got finitely many of these basis functions. So then we need to take our physics and project them somehow onto this discretized space. And I'm using hefty air quotes around project because I'm not going to go into detail on how that's done here. It's different for every PDE solver. For example, in FEM, you project through an integral operator across subdomains defined by these mesh elements usually. And in the finite difference method, you just discretize the PDE directly on the domain. But in any case, you do that somehow, and if your PDE is linear, you'd usually end up with a linear system. If you've got a nonlinear PDE, you'll have an objective function, which you're trying to minimize, to choose these weights that minimize this objective function. So this kind of links the discretized representation to the underlying PDE. And then we just have to solve the system, and we'll get a approximate solution. So the sort of catch here is that this incurs discretization error. So I've written down an approximate function, un. This is a finite dimensional object when the true solution to this PDE would live in an infinite dimensional space. We've discretized the domain, and we've projected the PDE onto this sort of discretized pair of function and domain. And all three of those operations can separately incur discretization error, which is something that can be very large. So for example, if we think back to this climate model that I had on the previous slide, this diagram here has on the y-axis spatial scales that phenomena that are related to weather and climate occur on, and on the x-axis temporal scales that these phenomena occur on. So in the top right here, we've got sort of climate level variations which occur over decades and on 10 to the 4 kilometer type scales. And right down here in the bottom left-hand corner, we've got turbulence, which occurs over seconds and at very, very small scales. So the point here being that sort of everything up here, up this diagonal, has an influence on the future evolution of weather and climate. But if we look at what climate models are able to resolve, at least as of when this figure was produced, we really can only see this top right-hand corner. So climate models, because they have to be implemented on computers, basically the best that we can hope for is discretization over time in terms of days, and discretization over space in terms of 10 to the 3 kilometers, at least over sort of long time scales that the climate models that we're interested in, this GCM here stands for General Climate Model, are expected to simulate over. So that's just a fundamental limitation of the computer hardware that these models are implemented on. And although things have improved, so if we look at what the resolution of these models looked like in the 1990s, we can see that Britain doesn't even really exist. So fine. Not important in terms of future climate variations. At least now Britain gets to be about 20 pixels. But clearly this is not resolving all of the details that are important for modeling what actual weather and climate look like in the UK or indeed in Europe. You know, we are really representing mountain ranges as tall 1-pixel blocks, and actually turbulence can occur as a result of the wind blowing around the structure of a mountain range, and that really has an impact on at least weather patterns in the next few days. So clearly, we need more resolution than we have access to, and this incurs a massive amount of discretization error. But the good news is that this is what probabilistic numerics is for, right? So if you've been paying attention for the first part of the talks today, then you will have gotten the picture that probabilistic numerics is designed to allow us to trade off computation for uncertainty. So we can reduce the amount of computational effort we put into solving something in exchange for a higher level of uncertainty in the result. So in the context of these problems, this might allow us to resolve some features of these PDEs. I won't claim that we'll be able to resolve the problem of how much of being able to see turbulence in climate models using probabilistic numerics. But if we're really only interested in stuff that lives in the top right up here, we might be able to, in a principled way, relax the amount of computational effort we put into computing those quantities while still being able to have a good understanding of how much error, how much uncertainty we induce as a result. But I don't want to give you the impression that this is all solved. Far from it. So that's why I've written, but there is a huge gap here. And I really want to emphasize that although I talked a lot about climate models in the first part of the slides here, we are really a very long way away from being able to work with climate models with probabilistic numerical methods, or Navier-Stokes in general. As far as I know, nobody has tried it. So, that's a call to action for all of yourselves, but also sort of a big motivation, because I think these are among the most important problems that we're working with at the moment in scientific computation. And I think there is if you say to a climate scientist, as I once did, that you'd like to be able to resolve your computational scales to the point where discretization error is negligible, they will laugh you out of the room. So there is clearly a sort of space for probabilistic numerical methods in this area, and I think this is why this should be and is an active area of research. Okay, cool. Is everybody motivated? Great. So let's go on to the sort of meat of the talk, which is how we produce these probabilistic PDE solvers. So in the first section here, I'm going to talk about how we can go from GP regression, which we've seen a lot of already, to the setting of solving a PDE. And Philip already gave some kind of hint as to how we're going to do this in his talk. widths, but I'll go through things again, just because that's how my slides are structured. Okay, so let's recap GP regression just so that we have in mind the same notation. So we've got a GP prior. So we're supposing that our unknown function u is distributed as a Gaussian process with some prior mean m and prior covariance k. To construct the posterior distribution, we write down some observations. So specifically, I'm working in a noise-free setting here, although we've seen the noisy setting a few times today, because if I have in mind the sort of future of talking about solving a PDE, it doesn't really make sense to think of the right-hand sides of those PDEs as being corrupted by noise, because they're functions that we can evaluate. So we suppose that we have observations of the form u of xi equals ui, uncorrupted by any noise. So fortunately, it turns out that we can still write down the posterior distribution in this setting. So this is our data set. And the posterior over u conditioned on this data, despite not having any noise, is again a Gaussian process. It has this mean, m bar, and this covariance, k bar. So the impact of the lack of noise on the observations here is just that where previously we had an inverse that looked like k plus sigma times I, now we just have k inverse. So let's look under the hood of where this result actually comes from and see if we can generalize this to a setting where we can apply it to PDEs. So basically, under the hood, if we work in a purely finite dimensional setting, so specifically, I'm supposing that I'm just interested in the joint distribution of u at two sets of spatial locations, given by x and x prime. This result comes from joint Gaussianity. So this vector containing the concatenation of evaluations of u at x and x prime follows a Gaussian distribution under the prior with this mean, so the concatenation of the two mean vectors, and this covariance matrix with the two Gramian-type terms that you would expect on the diagonal, and then the cross-covariances on the off diagonal. So the point is that because this is a multivariate Gaussian, this is a vector that is multivariate Gaussian distributed, we can use the multivariate Gaussian conditioning formula, which says that if I have two unknowns, u and y, which are distributed as a multivariate Gaussian, exactly as this is here, then the resulting conditional distribution has this form. So basically, if we take our Gaussian process regression example that we had on the previous slide, we look at these matrices and we map those matrices onto this formula, we get the conditional distribution that we had previously, except for that here I'm working with finite dimensional vectors, and there I was working with really functions. So I wrote these as functions here. So the key observation that allows us to get to a probabilistic PDE solver is that actually we can just do this anywhere where we get joint Gaussianity. So to do that, we need to generalize from observations that look like evaluations of the function u, so evaluations at particular spatial locations, to observations that are pushed through some, as Philip said in his talk, some information operator, some bounded linear operator that takes me from the function space, which I'm just leaving completely abstract at this point, calligraphic u, that my Gaussian process lives on, into r to the n. So we usually call these calligraphic A's that give me information about the unknown function u, the Gaussian process that I'm trying to condition. Information operators in probabilistic numerics. This comes from the paper that Jonathan Wenger mentioned that I wrote in 2019 on Bayesian probabilistic numerical methods. And explicitly, we're assuming here that this is an r to the n valued operator. So this is taking me from my unknown function and giving me finite dimensional vector, which tells me what I know about that function that I can then condition on. So the point here is that if A is a suitable linear operator, and as Philip said, bounded linearity is usually what we take, but this can be generalized a bit further. So this paper by Tadashi Matsumoto and Tim Sullivan recently gives slightly more general conditions on what operators A we can use. But if A is a suitable linear operator, then we again recover this joint Gaussianity. So we can show that the joint distribution of this vector of evaluation locations at this test set, capital X, and AU, where A is our information operator, is multivariate Gaussian. So I have some slightly weird-looking notation on the right over here, which we'll talk about in a few slides. But for now, let's just assume that we can realize these matrices that represent the covariance of AU and the cross-covariance between AU and U at the points X. In fact, I'm going to talk about this on this slide, so we don't need to worry about it for too long. So the previous slide had terms that looked like this. So this cross-covariance and this covariance of the image of U under this operator calligraphic A. The point is that these look like something that we might not be able to realize because we've got these A daggers here. So technically, these A daggers are adjoints. But again, we don't need to worry about this in the context of probabilistic numerics, because although sometimes it's helpful to sort of think of these in terms of adjoints applied to covariance operators, in terms of a practical implementation, these are just the operator calligraphic A, but applied to the second argument of the kernel instead of the first. So for example, if I was thinking of a kernel kxx prime, and my information operator was just going from this function space U, that my calligraphic U that my U lives in, into R, by taking the derivative and evaluating it at 0.5. Then if I applied this adjoint, A dagger to K, then I just get the derivative with respect to the second argument here, evaluated in the second argument at 0.5. It's a puzzled looking face there, is that? You okay? Okay, cool. So let's look at what that means in the context of GP regression. So here my information operator, my calligraphic A, just looks like evaluation of this function at the spatial locations ux1 up to uxn. And we can represent that using functionals that go from my function space into R as these evaluation functionals. So this, again, I think is notation we saw in Philip's talk. I'm just using this delta x1 up to delta xn to represent an evaluation functional. This is a functional that takes my function and just evaluates it at a spatial point. So then if I think of this in the context of this adjoint notation, then this, again, I'm just going to get back this covariance, this Gramian matrix kxx, because this A dagger is just taking my kernel function and evaluating it in the second argument at this set of spatial locations. Okay? Everybody good? Cool. So that leads me, again, to an equation that Philip showed in his talk, which is this general form of the Gaussian conditioning formula when I have this sort of suitable linear operator. And as every talk so far today has done, I'm going to say that this, I'm going to attribute Marvin here, who has made a significant impact on PN already, despite only being in the second year of his PhD. So when I originally derived some of this work, I basically just sort of assumed that this was okay by extrapolation from other works that were out there. Marvin came along and proved this in his paper from a couple of years ago on sort of formalizing PDE solvers, probabilistic PDE solvers. But in any case, this is what we've seen before in Philip's lecture, that this is what my conditional distribution looks like. And it basically has the same form as the GPU regression example that we saw, except for that we had to shove in some additional operators in sort of appropriate places. So again, by analogy with what we saw in Jonathan Wenger's talk and also in Philip's talk, if we think of this in terms of the multivariate Gaussian conditioning formula, i.e. in the setting of probabilistic linear solvers, these A's are just the S transpose, so the policy transpose applied to the matrix A that we saw in that talk, and the daggers just become transposes. Okay, so at this point, I sort of boldly put in this meme when I thought my Python code was going to be exciting for everybody, but now it turns out everybody's doing Julia, including even Philip. So, you know, we're going to see how a dinosaur codes at this point. At least I'm not showing you C++. So here we go. So basically what I want to show you here is just that actually it's not intimidating to implement these solvers. Modulo, there's a small amount of code which is slightly more non-trivial, but if you take that sort of non-trivial piece of code as given, the rest is really just, you know, a bit of data architecture and some linear algebra. So what I've got set up here, I'm not importing very much, just some basic Python libraries, and I'm also importing this module JAX-Solver, which I'll talk about. That's some bespoke code, which I'll talk about in a moment. So first we need to set up the problem. So let me talk about what the problem is first. So the goal here is, given a Gaussian process prior, U distributed as a GP with mean M and covariance K, which lives on the unit interval. I'm going to assume that it's at least once differentiable. Well, actually, I probably need, yeah, well, pathwise. Then I'm going to condition on observations that look like this. So I want to take condition on observations of the derivative of U at some spatial locations xi, and I want to condition on those being equal to U prime I, for I is 1 to n. So this is like the GP regression setting we saw already, except that instead of conditioning on the function values, we're conditioning on knowing the values of the function's derivative at some locations. So I'm going to start by setting up the problem, and this is where this sort of slightly non-trivial piece of code comes in that in order to be able to perform this conditioning operation, as we saw on the slides, we need to know how to apply this calligraphic A that's based on this differential du by dx to both the prior mean function, but more importantly, the prior covariance function. And in this notebook, I'm doing that by using this JAX-Solver.compile-JAX function, which basically is taking a symbolic representation of the kernel in SymPy. So here you can see I've set up the squared exponential kernel in one spatial dimension. It's a good thing Tony Carvonen isn't here, because you should look up from the last year's Spring School very extensive talk on why you should never use the squared exponential covariance function. But he's not here, so I'm allowed. Here I've got the A and the A bar, which are the implementations of this operator calligraphic A that we had on the slides. And you can see that what we're doing is A is just the derivative of this argument K with respect to the first argument X, so this guy, and a adj here is K differentiated with respect to its second argument Y. So this is where the non-trivial part comes in. This takes these A and A adj and applies them using SymPy to compute the symbolic representation of that derivative, then compiles it through JAX to give me something that I can actually evaluate in code. I say it's non-trivial, but you know, I have the code here. It's only 70 lines, so it's only slightly non-trivial. But it does represent somewhat of a restriction in what solvers we can sort of reasonably implement. Because in order to be able to compute these derivatives, firstly, the kernel obviously needs to have suitable regularity properties. But secondly, automatic differentiation often chokes on more reasonable kernels that I might be interested in, such as the Matern family, because they have an absolute value in their argument, or rather a norm in their argument in more than one spatial dimension. And the autodiff software can't handle that. So that's why I'm using the squared exponential here. You can hand compute those derivatives, they do exist, but at least so far we haven't, well, I think Marvin has found a way to automatically compute them, but he hasn't shared it with the public yet. Given this, we can access AKA, AK, and K itself from this sort of compiled system. So this is giving me my A adjoint that I had on the slides, and this is giving me my information operator applied to K, and then this is obviously just my kernel. And now I need to compute the, set up the conditioning problem. So here I have my test set. So this is the set capital X of locations that I'm going to be evaluating my GP at. The first thing I'm going to do is plot the joint distribution of U at these test points, so what we would usually be interested in GP regression, and AU evaluated at those test points. So that's what I have somewhere down here. I mean, in terms of the code, this is just to handle the gross deficiencies of the squared exponential covariance function. So I'm inverting and computing square roots by singular value decomposition. Again, don't use the squared exponential covariance function. But apart from this, this is really the only bit of sort of mathematically interesting code where I'm just setting up the Gaussian, the Gramian matrix that I need to take the square root of to get samples from the joint distribution over U and AU. And this is just plotting code. So if I run this, then it breaks. This is because, again, I'm such a bad coder. So if I run the notebook starting from the beginning in order, then we can see the blue lines are the joint distribution of the mean. So the mean of U and AU. We can see that they're both just centered at 0. And the shaded region is a 1 standard deviation credible set, point-wise. And then the orange lines are samples from these two, from this joint distribution. So if we run this a few times, we can see that we're getting something like sort of the derivative, and then we're also getting, something like the function and its derivative plotted for sort of different realizations of the randomness. Okay, so let's move on to conditioning. To condition on AU, I need a training set. So here I've plotted my training set. This is just based on 5 equally spaced points in this interval from 0 to 1. So I'm going to take my U evaluated on that test set, and I'm going to condition on the value of its derivative at just these 5 points. And I also need a true function to be able to construct some derivatives. And I'm just taking my true function to be sine of 2 pi x. So that's what I have plotted here. And of course, it's fairly straightforward to compute the derivative. So now we can construct the conditional distribution. So this is the data that I'm going to condition on. I'm just evaluating the derivative of this true function on the locations xa. And then we just have a tiny, tiny amount of code to write. So because, again, this AutoDiff software is taking care of computing these matrices for me, I just have to build the matrices and then compute the solution to a linear system using, again, a singular value decomposition to get both my posterior mean, m bar, and my posterior covariance k bar, and that's what's plotted at the bottom down here. So a couple of interesting things to observe. Firstly, let me scroll down so we can see the whole thing. Firstly, we're kind of matching the sinusoid almost exactly, right? So we've only got 5 in a mean sense. So you can barely see where the mean line is. It's this blue line here. Because it's almost right on top of the orange line. So in the eyeball norm, they're almost indistinguishable from each other. But we still have considerable uncertainty, unlike what we would have in the Gaussian process regression case. So we don't see this sort of characteristic squashing of the uncertainty near the observation points, again, because all we've seen about this function is the value of its derivatives. And in particular, if I upward shifted this function or downward shifted it by a constant amount, I would still get a function with the same derivatives. So the important thing here is that because I've only observed this derivative relationship and not the boundary conditions associated with proper PDE, I get this very, very wide uncertainty. So in the next few slides, we'll talk about how we can basically perform the notational task of taking this problem of just conditioning on the derivative alone and turn it into conditioning on the derivative plus the boundary conditions. But here's probably a good place to pause for questions. Everybody okay at this point, or are there any questions? Yeah?
I guess I'm just wondering, I guess say you had values of the solution at specific points and you conditioned at those, I guess what would the posterior look like?
That's an excellent question, which is, if you'll excuse me for 5 slides, I will have the answer to you in another notebook then. But that's a really good question, and that's exactly what we're going to do in the next part of the talk. Okay. So, part 3 of the talk is about taking this generalization of GP regression and turning it into a probabilistic PDE solver. And the sort of observation here is that we just need to adapt my operator calligraphic A to the particular PDE problem at hand. So we've really done all the hard work at this point. We know how to condition Gaussians on observations through suitable operators, with that asterisk in front of suitable. We just need to design the operator to kind of match the PDE and both encapsulate the physics, i.e. the derivatives that the PDE contains, and also the boundary conditions. And we should get a probabilistic PDE solver. So let's start by writing down a PDE that we might be interested in solving. So this is a PDE that's often called Darcy flow. Basically it describes the steady state flow of a fluid through a medium. So the unknown function here, u of x, this we could think of as being like the concentration of the fluid or the pressure of the fluid at every point in the domain. So if we were interested in, say, a problem in subsurface flow, where we had fluid that we knew was flowing through an aquifer, which is an aquifer is basically like a giant underground sponge, which is made out of rock that has lots, it's porous, so it can store fluid, and this is basically where the groundwater is. Then we might be interested in studying how a contaminant flows through that groundwater, and that would be described by this PDE. So here, kappa of x, that will be the permeability of this big aquifer, this big sponge. This is a spatially varying quantity to allow for the fact that maybe the aquifer is more permeable at certain points in the domain than it is at others because of how the structure of the rock under the surface changes. And we have a boundary condition here. Again, this is a Dirichlet boundary condition, as we saw at the beginning of the talk. So we're assuming that on the boundary of the domain, partial D here, we know the value of the solution everywhere. It's common to also use Neumann boundary conditions in these kinds of problems, but here we're just focusing on Dirichlet. And then this f of x describes any sources or sinks of fluids, so any like underwater springs that are coming from deeper under the earth, or places where water can flow, rainwater can flow down into the aquifer more easily. Have I said anything? Yeah. So we're assuming that we're given these three guys. So we're given the permeability field, at this point in the talk at least, and we're given the forcing and the boundary term, and we want to recover the unknown u of x using observations of those quantities. So for a very simplified version of this problem, which as a statistician, this is about the most complicated PDE I know how to solve, this is what the solution looks like. So here we have corner-to-corner flow. So we have, in fact, this is a case where we have Neumann boundary conditions. But here on the bottom and the top side of this box, we know that we have basically a linearly increasing concentration of fluid from, I think, 1 to 2, or maybe it's 0 to 1, I can't quite remember. It will be 0 to 1 because we know what the concentration is up there. And on the other top boundary of the domain, we have the inverse. So we have high concentration in the top left and the bottom right of the domain. And this kappa of x describing the permeability, we're just assuming this is a uniform medium, so kappa of x is just equal to 1 everywhere. Okay, so now let's start to work on building our information operator. So we've got, this is the PDE that we were interested in originally, but I've kind of abstracted it to help with notation behind these two operators, calligraphic L1 and calligraphic L2. So L1U is just the PDE operator that applies in the interior of my domain, and L2U is the Dirichlet boundary condition that applies on the boundary. So the overall PDE just turns into L1U equals F and L2U equals B on respective portions of the domain. So I'm focusing on just interior and a boundary condition here to simplify the exposition, but I just want to make the point that I could, in theory, introduce arbitrarily many of these different conditions, different PDEs, and the structure that is going to emerge on the next few slides gets a bit more complicated, but still is basically the same. Okay, so we have these two. I mean, I haven't really done anything at this point, right? I've just taken my PDE operators and hidden them behind some letters. So this doesn't give me an information operator because this is still L1 and L2 are still operators that go from the function space U lives in into a different function space. So to build an information operator, we need to make some assumption about how we're going to actually discretize the PDE. And in this slide, I'm going to focus on what's called collocation, which is where basically we take these two equations and we just evaluate the right-hand sides at some spatial locations to get our information. So we call in PDEs, we call this collocation. In GPs, if you just had L1 and L2 identity operators, you would just call it GP regression, right? We're just evaluating the function at some spatial locations. It's just that we have these slightly irritating continuous operators in the way, making the conditioning slightly more complicated. So let's have a look at a picture of our domain. So the blue line here is the boundary of the domain in this linear elliptic PDE that I showed a few slides ago, and the green box is the interior. So all this information operator is going to look like is we put a bunch of points inside the domain and some points on its boundary. So the green crosses are interior collocation points, and the blue crosses are boundary collocation points. And then we just build a data set, calligraphic D, by taking the union of the interior collocation points plus the function, the forcing function evaluated at those points, with the boundary collocation points plus the boundary function evaluated at those collocation points. So in terms of an information operator, if we again write down our PDE on the left, so we've got our L1U is F and our L2U is B, this allows us to build our operator calligraphic A by just concatenating or composing these operators with an evaluation functional, as we saw earlier. So here we've got evaluation functional for all of the points in the interior of the domain, the interior collocation points, and here we've got evaluation functional for all the points, the boundary collocation points. So our information operator calligraphic A naturally decomposes into A1, the bit of information from the interior, and A2, the bit of information from the boundary. Okay, so now this is again the conditioning formula that we had a few slides ago for how we condition our GP on an arbitrary suitable information operator. And this is the joint distribution that that's based on. So if we were just to match the structure to this slightly more complicated problem that we've got now, where we've kind of got two information operators, now we just still have a multivariate Gaussian. It's just it's got sort of blockwise 3 components. But the same kind of structure emerges, right? So specifically, if I match components here, these are the kind of Gramian style matrices that I'm inverting for the sort of general problem. And this just matches to this lower right block from this case where I've got the 2 information operators. And then the blue boxes here are the kind of, I don't know what you call them, the side operators that are applied to this, this Gramian inverted. So it's not super complicated, right? We just have, here we just have blockwise bivariate Gaussian, and here we have a blockwise trivariate, I guess, Gaussian. But these bottom 2 components, we can just sort of munge into this AU as we have up here. And that gives me my probabilistic PDE solver. And this is kind of uninteresting because actually this is just the equation that I wrote down a bunch of slides ago, highlighting the fact that actually building the probabilistic PDE solver, once we have that multivariate Gaussian conditioning formula or suitable Gaussian conditioning formula on function spaces, as proven by Marvin, is really just notation, right? It's just writing down a suitable information operator that we know we can condition on and then doing that. Okay, so now we have another demo. I couldn't find a Python meme for this one that I liked at least, but that's probably fortunate because again we're just doing Python. Where's my code? Here it is. So if we pop over to this other notebook now, this is very similar to the notebook that we had before. We're still solving a problem that lives in one spatial dimension. So my domain here is just the unit interval still. But now, in addition to having this interior condition, which on the previous demo was just the derivative, here we have the derivative plus this boundary condition that applies at either end of the domain. So the other complication is that we have this function which I've parameterized by the parameter theta. I called it kappa in my slides. I've unfortunately called it C here. But in any case, this is the permeability field, which describes how hard or easy it is to flow through various portions of the domain. So let's start by choosing a value for theta, which gives me a permeability field, and plotting what the permeability field looks like. So I've taken my permeability field to just be x with theta times x. So if I take theta to be equal to 1, as I have here, then clearly it's going to be easier for the fluid to flow through the left part of the domain than it is for the fluid to flow through the right part of the domain. If I set theta to be -1, and actually evaluate properly, then obviously we just get the opposite behavior. So let's put that back to 1. Now we have, as we did before, some problem setup. So I'm again leaning on this JAX solver.compile JAX, and I'm again leaning on this squared exponential covariance function because it's so wonderfully easy to differentiate. In terms of this sort of autodiff part, the only additional complexity is that whereas on the previous slide I had to pass in just one function, which was the derivative function, here I have to pass in both my interior and boundary conditions. So for this problem, it's kind of trivial because my boundary function is just an identity function. But by changing b and b bar here, for example, to be derivatives, I could equally use Neumann boundary conditions. So now we've got jacksolver.compilejax, which basically takes these 4 operators specified as 2 lists and forms all the pairwise compositions of them, of those 2 lists, to give me counting is hard, 6 functions, which are all of the sort of relevant pairwise compositions up to being able to transpose the matrices. So I've got KAA, KBB, KAB, KA, KB, and just K. Okay, so now if we keep going through this notebook, we can construct a training set. So here I've got n is 5 equally spaced spatial points, as I did in the derivative conditioning example, except for that here I've highlighted 2 of them in blue. So the blue points are the boundary collocation points, and all the black points are the interior collocation points where that interior condition is going to apply. So this gives me my partitioning A1, A2. The black points are giving me my A1, and the blue points are giving me my A2. For my test set, I have 51 equally spaced points inside the domain, I think. And at this point, I can just go straight to constructing the conditional distribution. So again, as I've said a couple of times, this is really just kind of architecture. We just need to construct the blockwise the block matrices from these multiple different applications of operators to the kernel, evaluated at the collocation points. That's what we're doing here. So you can see this matrix interior mat, perhaps could be called, more properly called Gramian. This is the matrix A, K, A dagger that I need to invert, and all of the other matrices are just the matrices that appear to the sides of it that we apply the inverse to. So this is just constructing the data. So inside the domain, I just took, I don't think I mentioned that the forcing was equal to 0 everywhere inside the domain, and we have the boundary conditions u of x is 2 at x is 0 and u of x is 1 at x is 1, which I can just form into this, again, blockwise, form into this vector y, which is the right-hand side vector that appears in the mean. And then with all of that done, all of these sort of complicated matrices assembled, all I have to do is just do a bit of linear algebra, and I get my posterior mean here and my posterior covariance here. So I can visualize that posterior mean and covariance, and I get this sort of wobbly looking function here, which we can see clearly satisfies the boundary conditions. So at x is 1, we get that the function is passing through 1, and at x is 0, it's passing through 2. That's because at those 2 points, this is literally just GP regression. So of course it passes through those points, and of course it has no uncertainty at those points. And then we've only enforced the PDE at these 3 locations inside the domain. So there's considerable uncertainty remaining, as can be seen by how wide the distribution is. But if I add a few more conditioning points, this is where we all need to hold on to our hats, because I'm doing live code. Not in this fancy way that Philip did it, but in my own hacky way. Then we can see that the uncertainty narrows so now I've gone from having just 5 training points, to having 10 training points. We get narrower uncertainty. And we can see this kind of trend that because it's easier for the fluid to flow through the first part of the domain than the second part of the domain, the concentration is higher in the first chunk of the domain than the second chunk of the domain. So the last thing I'll do is just show you what happens if I split this theta from 1 to -1. So now I'm making it harder to flow through the first part of the domain than the second part of the domain. If I run the whole notebook again, invalid value encountered in square root. That's because of my friend the squared exponential covariance function. This doesn't do what I wanted it to do, so that's the pitfall of live coding. I think maybe I just need more conditioning points. Okay, that's not doing what I wanted to do, so that's why you shouldn't do live coding. Cool. But in theory, what we should see is that the PDE solution, well, actually, no, this is doing what I wanted to do, right? So there's sort of, the gradient is higher in the portion of the domain where the permeability is smaller. So Good. Okay, I can still code. That's good. Right, let's go back to the slides now. And go on to the next part of the talk. Maybe I'll just pause here and ask if there are any questions before we do the tiny bit of theory. Everybody good? Okay, cool. Oh, sorry, yeah.
For the heat equation case where you also have time,
Yeah.
how would that change?
In principle, not at all. So you just need a kernel that's specified over both space and time. In practice, there are some cleverer things that you could potentially do if you knew that there was a temporal dimension, like some of the things that we're working on at the moment are based on modeling, using a state space model to represent this kind of structure where you've got like a more complicated spatial dimension. But yeah, in principle, nothing changes at all. Does that answer your question?
Yeah. And does it still perform as well? Because I can see like making predictions on a space, but when you make predictions against across time, it might be a bit more tricky. Like you might need more, but you can't get more points.
Well, so I guess I would argue that it maybe isn't more tricky unless the problem has some structure that makes it harder, right? So in a really homogeneous problem, like a really simple problem like the heat equation, I think it probably would be basically the same. But obviously there are lots of PDEs where the temporal structure is quite complicated and you have turbulence and things where, but again, the complexity is coming from the physics. And I think in terms of the solver itself, there's kind of no difference. Yeah?
Yeah.
Any other questions? Okay.
Can I ask a follow-up question?
Yeah, of course you can.
In terms of computational time in running these, how do they compare with say finite distance?
So that's something that I have indeed glossed over. We've had lots of comments on computational complexity so far, and I haven't mentioned any of them. So in terms of the complexity, of course, this kernel matrix that you have to invert is usually dense. So you'd get the classical cubic or near cubic complexity of GP regression. But the picture is a bit more difficult to kind of capture because finite differences, obviously, you have to invert a sparse matrix. So you win in terms of sparsity, but here it's possible to encode structure of the solution. So you can encode smoothness into your prior. And so the relationship between sort of computational effort and convergence order is a bit more subtle. But I wouldn't make the argument that you should use this over FEM because FEM, even though it converges at a lower computational order in general, is still much, much faster. And of course, the software is much more mature. Any other questions? No? Okay, all good. Cool. Right, so.
Maybe to add to this point, though, that FEM methods would also be captured in this framework.
Yes, so that was a point that I actually
They're
meant to mention in the slides, is that we focused on co-location, but Marvin has generalized this to, in principle, this operator A just needs to be a suitable operator, right? And FEM kind of information is completely compatible with that suitability. With the caveat that unless you had special structure in your prior covariance, you would still typically get a dense matrix out of using FEM-style information, but you'd still get the convergence order that your prior was giving to you as a result of the smoothness assumptions that you were making, I think. Marvin can correct me if I'm wrong there.
No.
Yeah.
So you can show that you can reproduce a lot of classical methods in the posterior. I mean, that is another way of looking at it, right? So you literally get exactly the same estimate as FEM, for example, with some of these methods.
So the sort of structure that's appearing here is that Gaussian conditioning and kind of linearity and linear subspaces are really intricately connected to each other. And often these kind of PDE-style solvers are really just constructing a solution that's orthogonal to a particular subspace where you have some information about the solution. So it's not particularly surprising that if you set up the prior properly, you can get the same thing as you would get from a classical solver because of that optimality, linearity, subspace style stuff that's floating around. But we can talk about that a bit more later if you'd be interested to.
Oh, sorry, Joe.
Yeah.
So this is
With difficulty, yes. Well, I'll talk about that a bit at the end, but with difficulty is the answer I'll give now. Okay, so we have a few small theoretical results here. Firstly, what about the uncertainty quantification? So in particular, what I'm showing in these slides is that in a worst case sense, so this is similar to a result that we saw earlier, in a worst case sense, the error, point-wise, is bounded above by the square root of the posterior covariance function. So this tells us that, again, in a worst case sense, the posterior covariance is a meaningful quantity. Let's just go through some of the assumptions that are required. There are some additional technical assumptions that I'm just not going to talk about, but at least in terms of the sort of intuitive technical assumptions that we need to make in order to get a result like this. Firstly, we need U to live in this Sobolev space of order beta. So beta we can think of as being like a smoothness that tells me how smooth my solution is. U is the unknown solution here, and we need beta to be bigger than d over 2. And secondly, that the RKHS HKD is equivalent to this Sobolev space. So if that sentence doesn't mean anything to you, then don't worry too much about it. It's basically just saying the GP is sort of compatible with how smooth the solution is. Then we can derive an error bound like this, which basically says that the error I make if I interpret my posterior mean as being an estimate of the solution, so this point-wise error, can be bounded above by this error in the RKHS norm, U minus M. So this is the difference between the two solutions of the prior mean multiplied by this square root of the covariance at that location. So that says that the covariance is, at least in a worst case sense, meaningful. And we can extend this slightly further, but turn it from a result that's quite abstract. So nothing from this result tells me that this k is going to be small. It could be a billion, in which case my solution is not particularly helpful. But we can turn it into a result that says something about the covariance being small using the concept of a fill distance, which I'm not sure whether anybody talked about so far. So luckily I have a picture here. So intuitively, in terms of a fill distance, what this means is it's the radius of the largest ball that I can fit into the domain without touching one of the co-location points. So here I've sort of eyeballed what I think the fill distance would be. You could probably make an argument that it should be down here, but in any case, this I think is the largest ball that you could fit into the domain, and this h, my fill distance, is just the radius of that ball. So that's the mathematical expression for it, and basically what we can show is that if rho is the differential order of my PDE, so that's how many derivatives there are, the maximum number of derivatives in any of the sort of equations that describe the PDE, then the square root of my posterior covariance can be bounded above by this thing, h to the beta minus rho minus d over 2. So remember, this beta was based, roughly speaking, how smooth my the level of smoothness in my prior. This rho is the differential order of the PDE, and this d over 2 is just something that's related to dimension. So what this is saying is that basically I get a contraction in fill distance. So if I can make my fill distance small, I make my posterior variance. Yes?
Is that true for ultrasound? Or just for...
Yes, sorry, additional assumption. Assume, I would probably have to go and check exactly what the assumptions are, but I'm pretty sure isotropic is one of them. I think it might even be that the... Do you remember Chris? Chris helped me to write this paper, but I can't remember off the top of my head what the assumptions on this kernel are, but I think we might have assumed matern.
I think this holds for anything that's equivalent to a Sobolev space, because if you can do this for one Sobolev, you can do for all of them by normal equivalence. So I think that's the key condition.
Okay, cool. But in any case, we lose. So we have rate of convergence that depends on how well I'm filling the space, but I lose some convergence rate over what I would get from usual GP conditioning, which is just this stuff. I lose an amount of convergence that depends on the differential order of the PDE. So basically, because I'm kind of doing GP regression pushed through an operator that's taking away rho levels of smoothness from my solution, I get a kind of convergence that's a bit like what I would get on that rho reduced space. Okay, so let's talk about a few generalizations of this. This is actually where I was going to talk about Marvin's paper, so we're citing Marvin again here. So we focused on point evaluation. We can make this much more general. In terms of the results that we have here, the first theoretical result holds more generally. So this is just, in fact, a general property of conditioning Gaussian random variables on operators. It doesn't even have anything to do with PDEs. As far as I know, these fill distance type links are a bit more complicated to establish for other information operators than those that are based on collocation points. So I'm at least not aware of any literature that establishes these kind of like results that are to do with some analog of how well you're filling the space if you're using something other than a collocation type evaluation functional. Would surprise me if you couldn't derive a result like that, but I'm just not aware that somebody has. Yeah?
So can you go back one slide? Rho be greater than beta minus t. But maybe this equality should be.
Yes, thank you, Moto. I think I can just. There we go. Thank you. Okay, so we've got 20 minutes left. In the last chunk of the talk, I just wanted to talk about how we can apply these kind of solvers in an inverse problem setting. How many of you are familiar with what I mean by a Bayesian inverse problem? Again, maybe about half. So we'll go through it somewhat slowly. I mean, it's really just jargon, right? Bayesian inverse problem is really just Bayesian inference. It's used a bit more commonly in the setting where the forward map is a PDE, is based on the solution of a PDE. But if you just have in mind that we're doing Bayesian inference, but there's a PDE involved somehow, then you're probably along the right lines. But in any case, suppose that we have data y that's obtained by applying a map G, calligraphic G, to some parameter theta, and corrupting it with some noise zeta, which I think I'm going to assume is Gaussian later on, but not on this slide necessarily. We want to perform Bayesian inference, so we're looking to calculate or approximate this posterior distribution, which is just given to me by Bayes' theorem. So here, I'm emphasizing that although usually when you wrote down the likelihood, you would just have P of y given theta, I'm emphasizing that this likelihood depends on theta through the map calligraphic G. And I'm also going to assume that inside G somewhere is hiding a PDE. So the thing that links my unknown parameter theta to the observations is based on the solution of a PDE. So if we think back to the notebook that we just saw, there we had this parameter, this permeability field for the Laplace equation that was parameterized by theta. That's the right kind of setting to have in mind. So the idea here is that if we want to solve this Bayesian inverse problem, we would usually need to employ a technique where we kind of explore the parameter space by traversing a set of different values of theta, and we compute this map calligraphic G of theta for each of those theta. Now, the catch is that because G involves the solution of a PDE, we would usually need to employ numerical methods to do that. And if we use numerical methods that give a high accuracy solution to the PDE, then we might obtain a posterior that looks something like this. So this is kind of what we might think of as being a good or well-calibrated posterior in Bayesian inference, because although it's theta dagger, assuming this was drawn from the prior, lies in a high posterior density region of the posterior distribution. But the catch is that in order to compute this posterior, we need to apply G, again, for each value of theta that we visit. And if we need to compute G to a high level of accuracy, and it's a very complicated PDE, that might take a very long time. So a tempting thing to do might be to take the map calligraphic G and take the the PDE solvers that were embedded within it and just turn down the accuracy, right? So use a coarser discretization of the domain to get a forward map that was faster to apply, and therefore accelerate the inference procedure to get a posterior faster. But if you do that, then it's possible to show that you can obtain posterior distributions that are still peaked to roughly the same degree as this high accuracy solution over here, but biased, shifted away from the true posterior mode. So a particular troubling thing here is that theta dagger lies in a very low probability region of the posterior, which is what we'd like to avoid. So where probabilistic numerical methods come in here is the idea is that if we replace our PDE solver that lives inside G with a probabilistic PDE solver, because that gives us a probabilistic description of how accurate the solution is in terms of if we interpret the mean as being the solution, we can incorporate that into this inference problem and obtain a posterior that's in some sense robust to approximation error. So that you can see how this posterior is widened to account for the fact that the solver that we're applying is not particularly accurate. The application that I'm going to show in a few slides is to a piece of industrial machinery called a hydrocyclone. So this is a hydrocyclone, or rather this bit is a hydrocyclone. And these are big pieces of industrial machinery that are designed to separate contaminants that are suspended within a fluid from the fluid that they're suspended in. And the way they work is basically just like putting all that fluid in a bath and waiting for a few days for all of the sort of heavier contaminants to sink to the bottom so that you can siphon off the fluid from the top. But of course, that would take a very long time. So in practice, we use these hydrocyclones, which do it much, much faster, but they operate on the same principle. So this is a simulation that I have. So how hydrocyclones work is that we inject the contaminated fluid at high pressure here. That induces a vortex inside the hydrocyclone. The sort of lighter fluid moves towards the outside, where it can be siphoned off. Sorry, the heavier contaminants move towards the outside, where they can be siphoned off at the bottom, and the lighter fluid stays in the middle, where it can be siphoned off at the top. So because of this sort of high-pressure injection, we accelerate that process that basically gravity is doing for us in the bathtub example to allow us to do this on a much, much faster timescale. So the challenge that we are intending to sort of address in this setting is that in order to control how fast we need to inject fluid through this part of the hydrocyclone just here, we need to monitor the contents. And because the outside of the hydrocyclone is opaque, or more generally, even if we had a transparent hydrocyclone, we wouldn't necessarily be able to see how separated the fluid was, because we only have like a side-on view, and that might be difficult to see through the contaminants anyway. We need to monitor the contents, and one of the approaches that's been proposed to do that is based on a technique called electrical impedance tomography. So now here, this is a cross-section of a hydrocyclone. You can see this beautifully hand-drawn contaminant that's just been injected somewhere over here, and the high pressure has caused it to rotate a bit around the domain, so we can see now the blob of most contaminant is over here. And to kind of detect where the contaminant is, again, this electrical impedance tomography approach that's been proposed involves placing electrodes around the outside of the domain. We pass a current through the electrodes and measure the induced voltage, and then model how those two things are connected to each other through, again, a PDE that's living inside this calligraphic G of theta. So this calligraphic, the PDE that lives inside this calligraphic G is actually very closely related to the linear elliptic PDE that we've already seen, except with more complicated, well, obviously a more complicated domain and a more complicated parameter, which I'm assuming is these thetas are what describe the shape of this contaminant inside the domain. That's like the permeability field, which now is just like a conductivity, describing how easy it is for electricity to flow through various portions of the domain. And of course, it has more complicated boundary conditions as well, because we're passing currents through electrodes. Okay, so the idea of how we can use probabilistic solvers within these kind of inference pipelines is if we take this likelihood, where now I've emphasized that this likelihood depends both on the parameter theta through g of theta, but that dependence is actually as a result of its dependence on the true solution to this PDE, u dagger of theta. If we have so usually what we would do is we would take our theta, build a PDE solver, which described this linear elliptic PDE as a function of theta, solve it to obtain an approximate solution and just plug it in here. If we have a probabilistic solution, we can instead construct this new likelihood, which I'm calling PPN, which is based on taking the probabilistic solution and committing a crime, which I talked to Marvin about how much I hate it when people do this just the other day. And here I am doing it myself. So this is the density of the solution, the PDE solution, which obviously doesn't exist because the PDE is a function and we don't have densities in function spaces. Natal is laughing at me right now. But in any case, we basically take the PDE solution and we marginalize it out to obtain a new likelihood, which is intended to be widened as a result of the additional variance that we have from having solved the PDE inaccurately. So in some cases, this can be done explicitly, and this is, I think, pretty much my last slide, which shows a sort of a visualization of what this looks like. So this is based on a paper from 2019 with Chris and Robert Ackroyd and Mark Girolami. And here is a posterior that I get represented in terms of its mean and its standard deviation if I have access to a very high accuracy solver, which might be very expensive to run. So we can see the contaminant was injected up there, over here, and has rotated a bit around the domain because we're a few seconds post-injection. So that posterior might be very expensive to obtain, but if we use probabilistic solvers, we can instead obtain this sort of spectrum of solutions represented by all of these different columns here. So these are going from least accurate through to most accurate. The point is that although firstly, this end is much cheaper to evaluate because the forward map is much less expensive to apply because it's based on a probabilistic PDE solver, which is fairly inaccurate. And if we look somewhere around the middle of this sort of set of pictures, we can see that at least qualitatively, we have a good idea of where most of the contaminant is distributed in this sort of frame a few seconds post-injection. We can see that there's a sort of high concentration region over here, and that the level of uncertainty in that where the contaminant is concentrated is represented in terms of higher variance in the posterior than we had when we used the accurate solver. Okay, so that's pretty much everything I had to say. I've just got a couple of conclusions, or one conclusion really, which is kind of a lead into Chris's talk tomorrow, which is one might be tempted to think of this as providing you with a blueprint for Bayesian probabilistic numerical methods. So we just need to specify an information operator A, and then we can construct our conditional distribution by just conditioning on the values of what A gives us. The catch is that this only really works for linear PDEs, as Moto mentioned earlier, because really what we're exploiting here is joint Gaussianity of U and A. And if we don't have that joint Gaussianity, then we get into this horrendous rabbit hole of trying to work with distributions that don't really have a closed form. And yeah, I won't go into too much detail about what's involved in working with them, but apart from to say that it's really a very open problem that is an area of active research. So working with nonlinear PDEs is something that's still very much a problem to be solved. So thank you very much. And are there any questions? Cool, okay. In which case, we have dinner and drinks arriving in about 5 or 10 minutes. If you haven't put up your poster yet, and you have one, then please do it in the room where the posters have been put, just across the hall here. Yeah, sorry.
Can I ask a question?
Yeah, of course you can.
So can you show the plot of the hydrocyclone results?
Yeah. With this one.
Where you have the spectrum
Sorry.
between
Trying to get
cheap
there.
to compute and expensive.
There's a way to skip all of these transitions, right? But I can't remember what it is. There we go.
So in regions where it's unlikely that the contaminant is,
Yeah.
it seems like there's also low very low uncertainty.
Mm-hmm.
Is there some intuition for why that is somehow easier to learn?
I don't have a good intuition for why it's. I mean, the coefficient is injecting a lot more. You know, that's affecting the operator that you're conditioning on, right? And so it's very possible for regions where the solution is higher to also have higher variance, which is kind of, the solution is larger to have higher variance, which is kind of, to some extent, what we're seeing here. But, I mean, this is really an empirical result. I don't have a good intuition for why that would be easier to learn apart from just, you know, that we're seeing magnitude effectively here, right? Yeah.
Yeah, I guess maybe depending on what you know about it, but like, you know, if you sample that posterior prediction during two observations, those samples won't be longer than satisfy the 32 sample publication. Is that true?
No. So if you sample, they will the samples will satisfy the PDE at the collocation points, but not away from the collocation points.
Well, yeah, okay, yeah, that does make sense, yeah, because you know, we get more conditioning.
Exactly, yeah.
Right. So, in the example in finance, like you mentioned, like Black-Scholes,
Mm-hmm.
like geometric Brownian motion, right? It's essentially like stochastic differential equation, right? So,
Mm-hmm.
Like here you only talk about like deterministic ones, but like any thoughts about like extending this one to stochastic PDE?
I believe there are some people working on it, but I don't know whether the work is public yet. But there are some people working on it. Did you have a question? No? Okay, sorry. I thought I saw you put your hand up. Yeah, go ahead.
Yeah, about the nonlinear PDEs. I was
Yeah.
wondering, like, it's pretty common if you have a complicated nonlinear PDE to just linearize it by taking small time steps.
Mm-hmm.
And that way, would that also circumvent the issue of like non-Gaussianity? Like if you make every step a small linear update?
Yes, I think so. In that, then you're really just conditioning on a linear operator and marching over time. With the caveat that I guess you're losing something by doing that PN is intended to capture, right? Because your posterior doesn't know about the discretization error in the operator that you. So it's definitely something that you could do, and it would describe discretization error due to your time steps given that linear dynamics, but the nonlinear dynamics are still not capturing the posterior. Does that answer your question?
I guess so.
So I think my answer, if I could phrase it a bit differently, is yes, I think you could definitely do that, and it will be an interesting thing to do, but with the caveat that, of course, you're missing a piece.
Yeah.
You have some additional discretization error that your posterior doesn't capture, which is not to say you shouldn't do it, but that it's something you need to be careful of.